Welcome to episode 20 of CipherVibe's end-to-end cloud security architecture course. API security architecture protects the contracts through which users, applications, partners, and services request cloud functionality. It defines who may call which operation, with which data, at what rate, and how failures are handled. We will connect its purpose, design boundaries, implementation path, failure modes, and evidence of effectiveness. Every cloud security layer relies on the ones around it. APIs depend on authentication, authorization, network edge controls, input validation, logging, DLP, and runtime protection. The gateway is a control point, but every downstream service must still validate its own authorization and data assumptions. Treat the architecture as a chain. A trusted identity requests an action, a policy makes a decision, a workload or data service enforces it, and telemetry records enough context to investigate later. The first building block is centralize the public API boundary. Use an API gateway or equivalent entry service to expose approved routes, enforce consistent authentication, route only to intended backends, apply versioning, and capture request metadata. Keep backend services private where possible, but do not assume the gateway removes their own authorization responsibility. The second building block is scope OAuth and tokens to actions. Use OAuth scopes, claims, and resource-specific authorization to express what a client may do. Validate issuer, audience, signature, expiration, and authorization at the service. Avoid all-powerful tokens and do not let a successful login become blanket access to every API operation. The third building block is validate requests and responses. Validate request schema, content type, size, fields, and business rules at the boundary and again where the data is used. Reject unexpected input, avoid leaking implementation detail in errors, and ensure responses reveal only data that the caller is authorized to receive. The fourth building block is control automated abuse. Apply rate limits, quotas, concurrency controls, and payload constraints based on client identity and endpoint risk. Design clear retry behavior, monitor abuse patterns, and keep emergency controls that can tighten a route without interrupting unrelated services. Use this reference pattern. Begin with an explicit policy that describes the permitted outcome. Enforce that policy at the closest reliable control point. Route decision and activity evidence to protected storage. Then give an accountable team a tested path to review exceptions, correct drift, and respond to violations. A strong API pattern places an identity-aware gateway in front of private services, enforces scopes and request contracts, adds rate controls, and requires downstream services to repeat critical authorization decisions. Implement this layer in a sequence that preserves evidence and limits blast radius. First, inventory API routes, owners, clients, data classes, and backend paths. Second, move public routes behind a consistent gateway boundary. Third, define scopes, audiences, and authorization rules by operation. Fourth, add strict schema validation and client-aware throttling. Fifth, centralize request, decision, and error evidence without logging secrets. Prefer pilots with a named owner and rollback plan over an unmeasured organization-wide switch. The best rollout is one where a normal workflow succeeds, an unsafe path fails closed, and the team can explain the decision from logs rather than intuition. Security architecture fails most often through assumptions, not dramatic movie-style attacks. First, relying on a gateway while backends trust any internal request. Second, using one broad OAuth scope for unrelated operations. Third, validating syntax but not object-level authorization. Fourth, rate limiting by source IP only when identity is available. A configuration screen is not assurance. Collect evidence that the intended control applies to the correct scope and that violations become visible. First, test unauthenticated, wrong scope, cross-object, malformed, and rate-limited requests. Second, measure authenticated route and schema policy coverage. Third, review API gateway and backend authorization logs together. Fourth, exercise key or client token revocation without a service outage. Test both normal activity and a safe negative case in an authorized environment. Record the expected decision, the evidence location, the owner who reviews exceptions, and the rollback method. Repeat after platform changes, new integrations, or major shifts in business use. For a practical exercise, design access for a fictional billing API where a support agent may view one customer but cannot issue refunds. Use synthetic information or an environment you own or are explicitly authorized to administer. Deliver a one-page diagram, a concise control statement, a list of expected audit events, and one test for an allowed path plus one test for a denied path. This artifact is more valuable than a screenshot because it explains the reasoning behind the configuration. Before scaling this layer, ask 5 review questions. Which assets, identities, or environments are in scope? Who owns the desired state and exception decisions? Which enforcement point can reliably apply the rule? Which records prove the decision and retain enough context for an investigation? And how can the organization revoke access, contain impact, or roll back safely when a control fails? Good architecture makes these answers explicit and testable. The key lesson is that API security architecture becomes dependable only when design, policy, enforcement, evidence, and ownership move together. Document the decisions you make, remove permissions and exposure that do not support a real requirement, and rehearse the paths that matter before an incident forces the lesson. Continue through the next episode to connect this control layer to the rest of the CipherVibe cloud security architecture.